This presentation is about forecasting hurricane impacts on coasts. My name is Ab van Dongeren. I work at Deltares in the Netherlands, and I acknowledge my co-authors from Deltares, from the US Naval Research Laboratory, from the USGS, and from IHE Delft. Coastal communities are threatened and damaged by large storms, which can cause flooding, erosion, breaching, and destruction of property. And in order to safeguard those communities, we have forecasting systems, which now typically include predictions of tide and surge, and also coastal flooding, and include some of the wave effects. But for computational reasons, they lack the more complete wave-driven physics, also morphological change, and uncertainties due to uncertainties in the forcing. And that's why we have started a project funded by NOP and ONR to improve these forecasts with better observations, inputs, and faster numerical models. So the objective is to provide a single daily forecast of nearshore wave and storm surge conditions, current sediment transport, morphological change, breaches, and also flooding and structural response. And we want to do this in a fairly large area, such as this, the Gulf of Mexico coast, the US Gulf of Mexico coast, where we will use a chain of models which are driven by best track COAM's meteorological forcing of wind and pressure data, which drive large-scale hydrodynamic models for the basin, for the Gulf of Mexico basin, and also for the Atlantic basins, which are composed of Delft 3D flexible mesh and SWAN, and also Sphinx models, which are then provide boundary conditions for total water level predictions by the BWARE system, and also large-scale flooding by Sphinx. We will do the morphological change using the Siren model and Cosmos Coast model on a large-scale area, so stretches of about 500 kilometers to the left and the right of hurricane landfall, and detailed morphological predictions using the X-Beach model. We will also provide uncertainties in the response due to uncertainties in the forcing, for which we will run ensembles of the hydrodynamic models. We'll look at two examples that we're working on right now. One application area is the Gulf of Mexico, where we will be looking at Hurricane Michael, which made landfall here in Mexico Beach, and we'll look at some results at that town in Florida, and also in Apalachicola and in St. Mark's in the Florida Panhandle. And we'll also look at the results for Puerto Rico, which was hit by Hurricane Jerry and Karen. And here is already an animation of a Delft 3D and SWAN model, which are provide boundary conditions for the Puerto Rico case. And on the left side, we're looking at a Delft 3D model for the Gulf of Mexico. Some of the results for those three locations, Mexico Beach, Apalachicola, and St. Mark's, where we see that the model is performing fairly well in red relative to the observations. You see some differences here. Mexico Beach, there are some wave-driven components which are not included in the Delft 3D model, which seem to give some underestimation, but if you filter the data, it looks already a lot better. We're dead on in Apalachicola. And because of the size of the COAM's wind field relative to the observations, we're over predicting the surge in St. Mark's. We're using these boundary conditions to drive overland flood models, such as the Sphinx model, which is a reduced complexity but fast computing flood model. It's based on the paper by Bates, who incorporated this in the LIS flood model, but we include subgrid features and also wave-driven flooding. And with the subgrid features, we can compute the water levels at a 200-meter grid, but using the 5-meter topographic data, which influence the conveyance of the flow. And here you see an animation of flooding in the town of Beira in Mozambique. And we've used this model now to construct area models covering the Gulf of Mexico. We also have them now for the Atlantic coast. And you can see that we can cover fairly large areas, 5 models to cover the entire Gulf of Mexico coast. And for the wave-driven flooding, we've composed or constructed a number of smaller models which are lining the Puerto Rico coast. Now, looking at some of the results, here's the flooding or the total water level on the Florida Panhandle. Here is Mexico Beach. This is St. Joe's Spit. And here you're looking at the water level due to the surge and the rain, because we can also take rain data from the COAMs. And you can see here at Mexico Beach, there's a peak water level that is caused not only by the direct hurricane forcing, but also the interaction between the water levels in the behind the spit here, which shows a depression, which sets up the water level here at Mexico Beach, which is a very interesting feature. And hat tip here to Rick Lutig of University of North Carolina, with whom we discussed this. Those are the water levels and the overland flooding. Next, we're going to be looking at the morphological change, for which we use the X-Beach model, which we have set up here for Mexico Beach, and also for St. Joe's Peninsula, the spit, which has breached during Hurricane Michael. Results are still being produced. We're also looking at the total water level in Puerto Rico. So here the surge and the wave models, they drive a total water level module called Beware, which produces the total water level due to run-up. And here you see the maximum total water levels up to about 4 meters on the north shore of Puerto Rico due to Hurricane Jerry and Karen. And here you see the time variation during that event. The next steps are to expand the model system, and we're going to do that with 2 other modules. One is called Siren, where a lot of profiles along the US coast are taken, and the morphological change of those profiles is computed with a large number of X-Beach simulations. They're tabulated and put into a Bayesian model so that we can produce probabilistic outputs of dune erosion, sand loss, overwash, and breaching. So the X-Beach simulations are stored in this table, and they provide a quick lookup for the response in a large area of coast due to storms. We're also coupling it to a shoreline model, which is developed by the USGS. Jean Vitusek of USGS in Santa Cruz has produced this model, which is produces the shoreline response. It's trained by satellite data, and we can couple it to our model system in order to provide ensemble shoreline projections along large stretches of coast. The next steps are further development of the modeling system, connecting all the model components that I just described, validation on Puerto Rico and on Mexico Beach in Florida. And then we're going to test the model system in real time for 3 hurricanes in the upcoming hurricane season. We're going to be further developing the method to compute the uncertainties in the surge due to uncertainties in the forcing. And in the subsequent years to 2023 to 2025, it's refinement, validation, and analysis of the performance of the model system. Thank you very much for your attention. Let me know if you have any questions.